Our technique allows us to interchange cameras and projectors, thereby enabling us to take images from the point of view of a projector. Suppose, for example, we have the following experimental setup. Here we have a scene that is imaged by a camera on the left and illuminated by a projector on the right. This is the image taken by the camera, which shows the scene flood illuminated by the projector. In our paper, we refer to this as the primal image. After measuring the light transport between the projector and the camera, we show that the flow of light can be effectively reversed using Helmholtz reciprocity. This means that we are able to generate an image from the point of view of the projector as shown here. This dual image shows the scene from the perspective of the projector, while the illumination is coming from the position of the camera. Note that this is the image synthesized by our technique. Dual photography is the process of measuring the light transport to generate the dual image. A simple example will help us understand how dual photography works. This scene is illuminated by a projector and the outgoing light will be measured by a photosensor. Suppose we light up a single pixel at a time in the projector and store the value measured by the photosensor as a function of pixel location. We do this for all the pixels in the projector. Helmholtz reciprocity specifies that the light transport will be the same along a light path, regardless of the direction of the flow of light. This means that the same value would be measured whether the light starts off at the projector pixel and goes to the photosensor, or if it starts from the photosensor and arrives at that projector pixel. The transfer of energy from one to the other will be the same in either direction. Thus, we can transform our projector into a virtual camera and the photosensor into a virtual light source. By putting back the measured values into the correct positions of the camera image array, we can form the picture that would have been taken by the virtual camera. The resolution of this image will be that of the projector. Replacing the photosensor with a camera allows us to capture the four-dimensional transport between the pixels of the projector and the pixels in the camera. However, scanning the projector pixel by pixel is very slow, since there are millions of pixels in a standard projector. To accelerate this process, we must identify pixels whose contributions onto the scene can be later separated and illuminate them in parallel. Our adaptive algorithm subdivides the projector image recursively to determine which pixels can be lit simultaneously. This allows us to capture the transport between a projector and camera significantly faster than with the brute force scan. On the left we show the projected pattern, and on the right we show the image captured by the camera. Because we have captured the complete transport function, we have the information needed to relight the scene. Here we sweep a beam of light across the scene as a post-process. Note how the caustics vary as the beam moves. Because the virtual projector is of the resolution of the camera, we can also project patterns of high resolution onto the scene, as shown here. By sweeping a beam of light across this box, we can see that we can capture diffuse-diffuse interreflections and reflections off specular surfaces. One area that has gained interest in the past few years is relighting with 4D incident light fields. To do this, we must capture the six-dimensional reflectance function that relates 4D incident illumination to our 2D output image. Traditionally, this can be done by measuring the transfer between a single camera and an array of projectors. Dual photography can accelerate this process tremendously. In our paper, we show that this setup is equivalent to one with a single projector and multiple cameras. Because cameras are passive devices, they can operate in parallel, and thus their transport to the projector can be measured simultaneously. Here we show the dual image of a scene that was acquired using a mirror array to emulate multiple cameras. We can step through a few of these light sources and see that the positions of the shadows change. If several lights are turned on at once, we can generate soft shadows. We can also calibrate for the positions of these light sources and thus add a virtual character that casts shadows onto the scene. Because the adaptive algorithm is fast, we can capture the 6D reflectance function using a single camera mounted on a gantry. Here we move the light source around in the dual image to show the differences in illumination. Finally, we perform an experiment to demonstrate that we can capture subtle diffuse-diffuse interaction. The projector is set up in front of a standard playing card, while the camera is placed so that it can see the back of the card and the diffuse page of a book. In this case, the light going from the projector to the camera had to undergo a diffuse bounce at the card and another at the book. The image on the right is what the camera can see under ordinary room lighting. It seems impossible that we could ever identify the card by simply changing the incident illumination. However, our framework shows that this is indeed possible. By scanning the pixels of the projector, we can generate the dual image. Here we see that the color of the book changes depending on the point on the card we're illuminating. After the complete transport has been acquired, we can generate an image of the card from the perspective of the projector.